Hello, welcome everyone to our pre-seminar. We're very happy to have Jiayuan Wang from George Washington University, who's going to do a pre-seminar on the Hurwitz action in complex reflection groups. Take it away.
Thank you very much for this invitation. So in the pre-seminar, I will introduce what's a Hurwitz action, what are the complex reflection groups, and then I will give you a little bit of overview of previous work that had been done in this area, and also introduce some terminology that I will use in the pre-seminar talk. Okay, and also stop me whenever there is a question. So let's begin with Hurwitz action. Let G be a group and build a tuple of L entries. Each entry is an element in the group G, and consider the following operation sigma I, where we focus on the ith and I plus 1 position. So we slide Ti plus 1 to the earlier position, and then change Ti a little bit and move that to the later position. So this is called a Hurwitz move. And immediately we see this operation is invertible. So in the inverse case, instead of preserving Ti plus 1 in the sigma I, then in the inverse, we just preserve Ti. And then this induces the Hurwitz action on the braid group of L strands, and it satisfies all the braid relations. So if the difference between I and J is bigger than 1, then the two moves, they commute. And if J is I plus 1, then we have this equality. And also there are some invariants about the Hurwitz action. So if we focus on the first tuple and multiply all the entries together, call that product G. So that product will be the same as we multiply all the entries from the second tuple, because these two terms, they cancel, and so they preserve exactly the product. So now we can treat this tuple as a factorization of G, and then say each of the entry is a factor of the factorization. And because in a single Hurwitz move, right, we are not changing really the conjugacy classes, so then one of the invariant is also the multiset of the conjugacy classes. Similarly, it also preserves the subgroup generated by the factors. So naturally, one can ask, for an element in G, how many orbits do its factorization form under the action? And also, when does it just have a single orbit, where we say the action is transitive? So here, if we have two factorization of the same element, and we can get the other factorization by applying some Hurwitz moves to the first factorization, then we say these two factorizations are in the same orbit. And if all of the factorization form a single orbit, I may call that element as Hurwitz transitive element. Okay, so today we will consider the action when G is a reflection group. So now I will introduce what are reflection groups. Start with a real case. So we have a real vector space, then a reflection is just a linear transformation that fixes a codimension 1 subspace, and a finite subgroup of the group of all invertible linear transformation generated by reflections. That's the finite real reflection group. One example will be the symmetry group. So here permutation acts on the space just by permuting all the coordinates. And in particular, the transposition is a reflection. It permutes the coordinates xi and xj. So it fixes the hyperplane where the two coordinates are the same. So here all the irreducible finite real reflections are completely classified. We have this symmetry group. So for example, in S3, we have an element that has this matrix form. So this corresponds to the one-line notation 2, 3, 1. And this is what we call a permutation matrix. That means for each row and each column, there is exactly one non-zero entry, and that non-zero entry should be 1. And also we have the sign permutation as one of the irreducibles. So for example, here, what this means is that we can change any number of the ones to -1. So then, for example, this will be one element in B3. And also we have the even sign permutation. So that means we can change any even number of ones to -1. So maybe this one. So for this reason, this is an element in D3, but this is not an element in D3 because here this has an odd number of -1s. Also, the irreducibles include the dihedral group and 6 exceptional ones. And turns out all of the irreducible ones in the real case, they are the finite Coxeter groups. Also, all of these groups, they have a geometric interpretation. For example, this is the symmetry group of the n-dimensional cube, and the dihedral group is the symmetry group of a regular polygon. And this H3, that's the symmetry group of a dodecahedron, just to name a few. So that's what real reflection groups are. And if we change this word from real to complex, then we have complex reflection. Here again, a reflection is a linear transformation that fixes a codimension 1 subspace, and then similarly, a subgroup generated by these reflections are called a finite complex reflection group. And again, all the irreducibles are completely classified by Shepard and Todd in 1955. Here in this big infinite family, we have G and Pn, where we require Pn to be positive integers, and then P divides M. So an element in this group is a n by n monomial matrix. So that means in each row and each column, there is exactly one non-zero entry. And also we have this extra condition where that non-zero entry should be a mth root of unity. And also the product of all those non-zero entry is a m over pth root of unity. And then besides this infinite family, we also have this 34 exceptional ones, and they are.
Sorry, Jiayuan, can I ask a question? So these,
yes.
So in this group GMPN, so these n by n matrices, so can they have like, so the entries are m root of unity, but can I have like multiple entries in each row and column, or is there? Oh, it's just any. Oh, it's any matrix like that.
Right, so they are monomial. So in each row and each column, there is exactly one non-zero entry.
Okay. Okay. Oh, okay. Thank you.
Right. And the 34 exceptional ones, they are denoted as G4 to G37. And all the irreducible ones from the real case we just seen earlier, the symmetric group, the sign permutation, the even sign permutation, and the dihedral, they're all absorbed into this infinite family. And then the 6 exceptional ones, they're also absorbed into this 34 exceptional ones. And
so for example, so in the first one, in SN, every entry is it's just one.
Mm-hmm.
So it's a permutation. Okay, and then you are meant. So how do you for BN and DN? How do you so how do you keep track of that there's an even number of -1s in these parameters? Could you maybe? So why G to N makes sure that there's an even number of ones, for example? Or an even number of -1s? Sorry.
Yeah. So here we have this requirement of the product of non-zero entry. So if we're in 2 to n, then we require the product to be a 2 over 2. So 1th root of unity. So then the product has to be 1. So that immediately restricts the number of -1s we can have, which is an even number of -1s. And that only happens. Yeah, and then but here in type Bn, then the product is a 2nd root of unity. So we can either have an even number of -1s or an odd number of -1s. Both of them are okay in 2-1n.
Thank you.
And let me talk about a special group in this infinite family when p equals to 1. So in Gm1n, this is the Reith product of the cyclic group Z mod Mz with the symmetric group. And we can count how many elements are there in this particular group. So take a permutation matrix. We have n non-zero entry. Each non-zero entry is a 1. But now in Gm1n, instead of having 1, we can have 1 zeta square and all the way to zeta m -1. And these are exactly the m different mth root of unity. So then for each non-zero entry, there are m choices. And because there are n non-zero entries in the permutation, so we have m to the n, and there are in total n factorial different permutations. So multiply that by n factorial, and that is the size of this group, Gm1n. So this group is almost asymmetric group, but the difference is that for each non-zero entry, instead of just having one, we now have more choices. And in this particular group, we have two different types of reflections. The first one is the transposition-like. So this is called transposition-like because the underlying permutation here is a transposition, and all the sigmas, they are primitive root of unity, and the exponent here have choices. So the order of a transposition-like reflection is 2. And the second type of reflection we have is called the diagonal one, because diagonal-like reflection, because this is a diagonal element. And so for this type of reflection, the order here may be bigger than 2, depending on what this exponent is. So that's what complex reflection groups are. And now let me give you a little overview of the history in this area. So it all started with Hurwitz in 1891 in his study of the coverings of the Riemann sphere with given monodromy. So he studied transposition factorizations in the symmetric group. And then Kluman, Benezak, and Teicher, they give like a complete classification of the Hurwitz orbit of the transposition factorization of any arbitrary element in the symmetric group. So, and they use this graph-theoretic approach. So instead of looking at a factorization, we can look at a graph with the vertex set 1 through n, and then each edge connecting vertex I to vertex j, they correspond to a factor or transposition ij in the factorization. And they show that the action is transitive on minimum length factorization of a permutation. So here for a permutation to compute is minimum length, or sometimes I will call that reflection length, we can use this formula. So that will be n minus the number of cycles in this permutation. And yeah, go ahead.
Oh, so then, so transitive, so there's only one orbit of the...
Yeah, that's exactly right. All the possible minimum factorizations, so all the others can be generated by applying some sort of Hurwitz move to one fixed factorization. And then Bessis in 2003 showed that in a finite real reflection, the action is again transitive on minimum length reflection factorization of a special type of element called the Coxeter element. And then he generalized this result to the complex setting. So this is part of the ingredient of the proof for the K-pi1 property for complements of finite complex reflection arrangements. And the motivating theorems for today's talk, the first one is the 2003 one of Bessis that we just seen in the previous slide. The next one is by Baumeister, Gobet, Roberts, and Wegner in 2017. So they show that in a finite real reflection group, all the Hurwitz transitive elements, they are the parabolic quasi-Coxeter. So this is a bigger collection of elements, so it's not just the Coxeter elements. So this motivates us to try and find a similar characterization of Hurwitz transitive elements, but in the complex setting. So that's what we're trying to do. And before we talk about that, I will just do a little bit discussion about what minimum length means. So superficially, minimum length is just a number, the smallest number of factors we need in order to factor an element. But because we're working with reflection groups, so then there should be some geometric interpretation about the minimum length or reflection length. And indeed there is. So Carter in 1972 showed that if G is a finite real reflection group for any element, the reflection length is the codimension of the fixed space of that element. And then Shi in 2007 showed that in GM1n, the reflection length of an element is also the codimension of the fixed space about that element. But Foster and Green would show that for any other irreducible complex reflection group, the reflection length is not equal to the codimension of the fixed space. And in fact, we can always find elements in the groups whose reflection length is bigger than the rank of the group. So at the end of the pre-seminar, I will give you an example of such type of element.
Oh, so because if you're equal to the codimension that of the fixed space, that has to be less than or equal the rank.
Yeah.
Okay. Thank you.
So now before we get into actually computing reflection length, let me introduce some notation and vocabulary. So here we have a element in G615. And instead of writing matrices every time, we use this bracket notation. So the first part is the underlying permutation of this element. And this part is the exponents of the non-zero entries in each column. So here we have 1, 4, 0, 3, and 0. And these are called the weights of the entries. So an element is in GMPN if and only if the total weight is a multiple of P. So in this example, the total weight will be 1 plus 4 plus 3, which is 8. And 8 is a multiple of 1, so that element is in G615. It's also a multiple of 2, so that's also in G625. And for the same reason, it's not in G635 or G665. And we can talk about cycle of the element. A cycle of the element is just a cycle of the permutation. So in this example, we have 2 cycles, 1, 2, and 3, 5, 4 in the cycle notation. And the weight of the first cycle, we just add the weight of the entries together. So that gives us 5. And the weight of the second cycle, add all the weights together. So that's 3. With the cycle weight, we can talk about cycle partition. Cycle partition is just a set partition of the cycles. So we are putting the cycles into different parts. The rule is that each part should have weight a multiple of P. So in this example, if we are considering it in 615, so we can definitely put the 2 cycles in the same part. So that will be 1, 2, and 3, 5, 4. And the weight of that part is just the total weight of the element, which is 8. This is allowed because 8 is a multiple of 1. But we can also put the 2 cycles in different parts. So that will be 1, 2, and 3, 5, 4. And the weight of the first part is 5. The weight of the second part is 3. So this is also a cycle partition that is allowed. So here we see for an element, it may have multiple cycle partitions, but this element is also in G625. And in this group, there is only one possible cycle partition. That is when we put the 2 cycles in the same part. So we have 1, 2, and 3, 5, 4, and that part has weight 2. This is allowed because 8 is a multiple of 2. And with that, just 2 more words. The size of the partition is just a number of parts in that partition. And the value is the size plus the number of parts of weight 0 mod n. So now we are ready to present the reflection length formula from Shi in 2007. For any element in G and Pn, the reflection length is the minimum of this quantity, which is n plus the number of cycles minus the value of that of a partition. So to find the minimum of this quantity is the same as finding the maximum of this quantity. And let's try to apply this formula in the symmetric group. So in Sn, which is also G of 1, 1n, suppose we have an element that has some number of cycles. So here the weight of each cycle is 0, and that satisfies the requirement, right? The cycle of each part is a weight 0 mod n. So then to find the maximum value, the partition, we can just put each different cycles in its own individual part. And here the maximum value of this partition is just the number of cycles of this permutation. And then to apply this formula, okay, so we're not quite there yet. So the value is the size, which we have here, which equals the number of cycles, plus the number of parts of weight 0 mod 1, which is also the number of cycles. So the maximum value is twice that. And then to apply the formula, we have n plus the number of cycles minus twice the number of cycles, which is n minus the number of cycles. So this is the same formula that we have seen earlier. So this works in the symmetric group. And now let's look at a more complicated example. This is a diagonal element in group 424. And here are all the possible cycle partitions that follow the rule that each part has weight a multiple of P. And now let's compute all the corresponding values. The first part is just the size. So the first one has size 3, this has size 2, this has size 2, 2, and this one has 1. And now we just need to count the number of parts of weight 0 mod m. Well, here m is 4. Okay, so in the first cycle partition, the weight of the first part, that's 2. This is also 2. This is 4. There is one part who has weight 0 mod 4, so we add 1 to it. And then for the second partition, both parts have weight 4, so then we add 2. The next one, the first part has weight 2, the second has weight 6. No part has weight 0 mod 4, so plus 0. Exactly the same thing for the next partition. In the last partition, it has weight 8, which is 0 mod 4, so plus 1. And now we can see the maximum value is 4, and there are 2 cycle partitions that reach that maximum value. And here the reflection length for this element will be 4 plus the number of cycles, which is 4, minus a maximum value, which is also 4, and that gives us the reflection length 4. So this is how we can apply Shi's formula in finding reflection length of any given element in G and Pn. Also, what this sort of implies is that given any cycle partition, we can find factorizations that would have this number of factors. So now I will show how, given a cycle partition, we can build a factorization. So in this example, this is an element in G6-10. It has 5 cycles. Here are their weights. We can do a cycle partition where the first 2 cycles are in the same part. The last 3 cycles are in a different part. And the weight, so then there are 2 parts. That's why we have 2 here. And the weight of the first part, that's 2. And the weight of the second part, that's 6. So there is one part whose weight is 0 mod 6, so add 1 to it. And then apply the quantity there. We have the rank of the group plus the number of cycles minus a value 12. So this suggests there are factorizations of 12 factors. And now I will show you how we build that. First here, all these blue factors, they correspond to the blue edges in the factorization graph. And so here, these 2, they have transposition 1, 4. So that's why we have a pair of parallel edges connecting 1 and 4. And then in this diagonal reflection, there is a non-zero weight at the 4th coordinates. So here we have a loop at vertex 4. Then these 2 connecting 6 and 8, and these 2 connecting 8 and 10. So what these blue factors do is that they give us a diagonal element. And notice that here, all the non-zero entries in this diagonal element, they are exactly the weights of the 5 cycles. So what we have here is that we build a diagonal element that distributes the non-zero weight to all the cycles that are in this element. But we haven't actually factored the cycles. So that's what we'll do next. All these blue, all these green edges, they factor the cycle. So here, these 2, they factor the first cycle, and this one factor the second cycle. This is the 3rd, this is the 4th, and the last one, because it's a singleton, so there's no green edges connecting the vertex 10. And this factorization has exactly 12 factors. And notice that here, there are, in this factorization graph, there are 2 connected components. Each connected component, they correspond to a part in the cycle partition. And for each of the cycles, there is exactly 1 vertex that is incident with the blue edges. And if the weight of the part is not 0 mod 6, then we add a loop there. So these are some of the things we can say about the factorization graph. And if we look at this just for a bit more, we will realize that this is actually the maximum value. And so there's no possible cycle partition that will give us a bigger value. So that means this is actually the reflection length of this element, and 12 is bigger than 10. So this is exactly the kind of element that Foster-Greenwich discussed in her theorem, where we have elements whose reflection length is bigger than the rank of the group. And with that, I will end my pre-seminar.
Let's thank everyone for the seminar. Are there any questions?
So for instance, the maximum length that you can get, what would that be equal to? If you have a group of rank n, what is the maximum possible length there?
Oh, if we have n, then I would say we could have all loops, so that will immediately give 2 times n minus 1. Is it possible that we also have a loop? So, okay, so I want to say 2n minus 1 is probably going to be the maximum reflection length.
Okay, that's cool.
Other questions? So these green numbers here are producing the cycles, but then there are some weights, and you just get those so that it works out, or like the weights of the green factors.
So the weight of all these green factors, they all have weight 0 because they are transposition-like reflections, and that by definition has zero weight. So then, but so in order to have non-zero weight to all the cycles, we build a diagonal element, and that just corresponds to all these blue edges. So all of these do is that they assign the non-zero weight to all the cycles.
Okay.
Yeah, so in your figure below, the labels are not the weights, they're the positions of the reflections in the factorization, right?
Yeah, these labels correspond to where they are in terms of the factorization, not the weights. Yeah, that's a good point. Thanks.